Hello friends, welcome to Misostudy video classes, and today we are going to start a topic which is so useful that you can use this particular theorem or relation or concept or principle to find so many correct answers for so many questions. It means, is it really an important topic? Okay, let me mention the topic, you will realize yourself the importance and interesting aspect of this topic. Basically, we are in the mid of like you can say magnetism and moving charges, current flow, all these concepts. So, here the topic name is somehow like Ampere's law. Fine. One was Biot-Savart law that provided us with an you can say tool with the help of which we can find out the magnetic field associated with any type of current flowing conductor. Fine. Maybe it is a straight wire, maybe it is a circular wire, maybe it is a triangular wire, and so on so forth. Now, this is the law which enables you to find the magnetic field associated once again with what? That is current carrying conductor. Now, the first question that comes in your mind, what is the difference then this Ampere circuital law and this Biot-Savart law? Fine. So, for Biot-Savart law things were like distribution of the current was important and also the angle theta was important. Here situation is different. Now, first I would like to mention mathematical formation or expression for this law, that is B dot dl is equal to mu naught I. Fine. So, on the basis of this I will write down a simple definition, that is the closed interval, the magnetic field associated with a infinite long wire, say for example the magnetic field associated with a current carrying wire is mu naught times the total current in wire. Fine. Now, statement is simple, you can say only we provided wordings to this particular expression, that mathematical expression. Fine. So, now let us try to visualize this with the help of a simple example. Let us say I have this plain duster, okay, and there is a small hole in this duster and then this chalk holder is inside it. So, some portion outside of it, some portion over here. Now, it is visible like this. Fine. And this wire carrying some current. So, problem is to find out the magnetic field in this plane of duster. Fine. At different distances. So, now I will try to draw this particular diagram. Let us say this is the plane of this duster which I created, and then I have this wire. Okay. Why the wire is not visible over here? Because some portion passing through this plane. Fine. Now, at this particular point of time, let us say I am creating a circle like this. Fine. And current I is flowing in the wire and the radius is R. Now, this circle, this circular area is imaginary. Fine. After explaining this, I will also prove, I will also suggest, I will also say that this law is even applicable for any orbit shape. Okay. So, first start with the simple possible this shape, that is circle. So, let us say this point is O, let us make it slightly bigger, so that you can, if watching this video on your mobile, you can easily find this difference. This one, this is the center of the circle, this is the wire going on and then visible over here outside. Fine, this portion is hidden and current I is flowing, radius of the circle is R, and the name of this point is O. Now, in this situation there are 3 possibilities. First is, let us say a small distance dl, fine, this small distance dl, okay, and name of this like x, y. Now, over here if the current is flowing, then magnetic field associated how much, that we can find out, okay, in this particular plane. So, this visualization, as I mentioned here, now I will remove it and write down the formula. Now, you can see that this is a vector, this is a vector. It means in next line I can write down B dl cos of theta. That theta is what? Theta is the angle between this B and length dl, small length dl, okay. So, B dot dl cos theta is equal to how much? Mu naught I. Okay. Now, I will take the help of Biot-Savart law. Now, the Biot-Savart law is, I will use a different color chalk to show you, that B is equal to mu naught upon 4 pi I del L sin theta upon R square, I del L sin theta upon R square. So, for infinite length conductor, current carrying wire, this result is B is equal to mu naught upon 4 pi, then this I upon R square within bracket sin phi 1 plus sin phi 2, although I should not write it because already I provided a video based upon this Biot-Savart law, and my assumption is that you are revising, but it may possible that few students are new for this video or few of you not revising despite repeated requests. So, for the sake of that simple relation, herewith I am mentioning this. Now, for infinite length of wire, for infinite length of wire, phi 1 is equal to phi 2 is equal to pi by 2. This is something which also I explained in that particular video. So, if I will put sin pi by 2 plus sin pi by 2, then what I will get? I will get B is equal to mu naught upon 4 pi, B is equal to mu naught upon 4 pi 2I by this R square, fine, 2I by this R square, this term that is coming over here as R. So, now you can find it that dl and this R, so finally you can write down R, fine, you have to manage this dl and R square. So, directly I am mentioning this result. Now, this result is true over here also, but what is the beautiful aspect? Beautiful aspect is this is the value of B, and what we will do, we will use this value of B in this particular relation, fine, integration part. So, basically we are trying to prove this this Ampere's law. So from here what we will say, phi, rather than b I will write down mu naught upon 4 pi 2I upon r into cos of theta and dl. Now for cos of theta you can say plus minus value is 1. So for the time being need not to consider it. Fine. So simply say dl. Okay. Now mu naught 4 pi 2I r, this all is constant. So obviously it will have to come out as mu naught upon 4 pi. And one more important aspect over here, moment you are writing these type of relations, so wait for few seconds, try to recall the values and dimensional formula, because normally in exams in 1 or 2 marks question these type of expressions come and they ask what is the dimensional formula for that. So if at that point of time you will start finding the dimensional formula, going to be difficult. So let me allow to put it in a bracket, that is just showing you the importance. Dimensional formula of this quantity, please know that. Now as mu naught upon 4 pi and 2I by r all constant. Now why constant? I am telling you. Reason is the amount of current flowing fixed. Radius r, I mean the distance at which you want to find out the magnetic field, that is also fixed unless and until you are not changing, and then this is a constant term. So do one thing, put all these things outside. Okay, no problem, we will do that. So what I can say in this particular expression, that is mu naught upon 4 pi 2I by r within bracket dl. Now the problem with dl is what? Okay, take a look over here. Let us say it is a circle of radius r. So that complete circumference is going to be how much? 2 pi r. Fine. So similarly this 2 pi r, that will give you the same result, 2 pi r. Fine. Pi pi cancel. So what the result you will get? It is 2 pi r, putting the values by using values of this dl, we can say this entire expression, this much, is nothing but mu naught I. So this way you can say we provided a proof for that. It is not a proof, it is basically you are moving step by step of explaining this result. Fine. Here you are finding the value of B using Biot-Savart law, but still that question is in my mind is not clear. Why we are learning Biot-Savart law? Then again we are learning Ampere circuital law. Why we cannot use this Biot-Savart law wherever I am trying to use Ampere circuital law? Fine. Yes, this question is quite natural if coming in your mind, and the answer of this question gradually is going to be clear to you. Fine. Once you start doing some practice, start you can say analyzing these aspects associated with this particular result. Now after this, I would like to mention application aspects of Ampere's circuital law. Fine. So it is application of Ampere's law. Fine. Now, what is the first application? Fine. But before that, I think I should write down that line which I mentioned in the starting of the lecture when I was drawing the diagram. So, just consider this line as a, it is also the part of that application, and the line should be this law, I am coming on to the application part, but just read it. This law is important line, applicable, this law is applicable to even any orbit shape closed path or closed circuit. So, what is the meaning of this these four white lines? The meaning of these four white lines is this way. Once again, consider the same situation. Fine. Wire is going like this, coming out over here. So, if rather than circle, I am creating an amoeba like this. Fine. You know, I am sure everyone aware with this creature, one cell creature, amoeba, something like that. So, even in this orbit shape, this law is applicable. Fine. So, you can say the freedom with this law is because of no theta involvement, which I mentioned even one single point for the Biot-Savart law, that this expression for magnetic field is theta dependence, which is not applicable for electrostatic fields. If you are regularly watching our lecture, then definitely you can notice it that it was mentioned over there. Fine. So, this white color equation explanation and this diagram. Then directly I am coming on to this application aspect. Sometimes I noticed these type of statements in medical entrance exams, or you can say in JEE mains exam, they mention 4 statements and the question was like, which statement is correct? So, there simply they mention the application of this Ampere circuital law is possible even with orbit shape. It is correct. Fine. Now, first application is, that is magnetic field due to long current carrying wire. That is magnetic field due to long current carrying wire. Now, you can say what is the meaning of this? One side you are saying application of Ampere circuital law, then you are saying magnetic field due to long current carrying wire. Yes. If you are interested to find the magnetic field due to a long current carrying wire, then it is because of this application part we can find it out. Fine. So, let us try to find out how we can use it, although I mentioned this particular thing over here. Now, the idea is, one is B is equal to mu naught upon 4 pi, and for the time being I am not writing these terms. Let us say I have a wire of any orbit shape and the length of the wire is enormous. Infinite means we cannot measure it. Fine. And then for this small portion like this, you want to find the magnetic field at any point P situated at angle theta. Now, you can say yes, this is something that we learned during the discussion of the Biot-Savart law. Fine. Now, over here we can do one more thing, although already I mentioned, that is there are 2 possibilities for the angle. Let us start moving this point here, here, or maybe possible someone will say the point is here. Fine. So, let us say consider this situation, that is I by R. Fine. Exact formula is what? B is equal to mu naught upon 4 pi I del L sin theta upon R square. But here we are trying to find out this value. Fine. So, mu naught upon 4 pi I upon R. I upon R means current in the conductor and R is the distance of the point from the current carrying conductor. Simple. So, within bracket once again sin alpha plus sin beta. That is sin beta. Now, infinite means, let us say a wire is going in front of my eyes till large, very large distance. Fine. So, for any point, if I am watching like this, I can say the point is situated at this way, up, down, anywhere like that. So, the value for alpha and beta is pi by 2. Fine. So, the value alpha is equal to beta is equal to pi by 2. Fine. And in this scenario, B is mu naught upon 4 pi 2I by R. Repeatedly same things I am trying to elaborate, tell you again and again, so that if you are just watching this video at least 3-4 times, then you can say yes, these things are simply clear in my mind. Fine. So, this is one aspect. You can also write it like mu naught upon 2 pi I by R. And this is the general relation for magnetic field around a current carrying conductor, with which we started our basic discussion of this chapter, moving charges and magnetism. Now, students, one more important aspect associated over here is that you can say second part of the application, that is application. Fine. What is that? I would like to mention a name over here, CATION, and that name is solenoid. Actually, this law you can use to find the magnetic field associated with a solenoid. Now, first question comes in mind, what exactly a solenoid is? Okay. So, I have a simple arrangement to show you this solenoid. Actually, in books, I am sure you must have noticed that the creation of the solenoid is using this type of, you can say, cardboard hollow cylinder. So, it is a cardboard hollow cylinder, I am sure is visible to all of you, and with the help of this small stick, I am just trying to show you the axis of this solenoid. Fine. Coming out like this. Then I am taking a wire, insulated wire, and then I hope there are two ends visible to all of you. This one is blue end and another one is a red end, slightly blue, slightly red. So, let us start wrapping the wire. It is not very long, just few turns, 1, 2, 3 and so on like that. Now, just take a look. Every next wire is on the top of the previous one. So, do not you think it is a helical arrangement of the wires wound around a hollow cardboard cylinder? Let me repeat my statement. Helical arrangement of insulated wire around a hollow cardboard cylinder. Fine, like this. Now, do one thing. Connect this blue portion, end, and this red end to the source, to the battery, positive negative terminal. What will happen? Current will start flowing. If the current will start flowing, accordingly magnetic field will also come into picture. So, there are two situations. One is on the axis of this solenoid, straight solenoid, and another is at any point inside, and then third possibility, which is not so essential, outside of this. Fine. Now, insulated means these wires arranged in helical pattern cancel out each other's presence. So, only at the axis you will get the magnetic field. So, first point I should write down about solenoid is, although I show you this simple device, so that visualization is really something which is very simple. solenoid is an arrangement of insulated wires on a hollow cardboard cylinder. Okay, the way I explained. Then obviously you have to find the magnetic field closed. Okay, so this Ampere circuital law is applicable only for closed integral. Fine, because of the reason of this mathematical expression. So I will write down B dot dl is equal to mu naught n l I. What is L and what is N? Good. Well, once again take the look of this magical device. L is the length of this cylinder, fine, and N is the number of turns of this wire. Over here I hope 4 turns are visible, 1, 2, 3, 4, so on. You can find about this situation. Now ultimately what will happen? This dl is nothing but total length, fine. So here you can put the values like B into this, let us write down the mod value, BL is equal to mu naught NIL. Therefore, this L and L will be cancelled. So for a solenoid, just take a look the expression, for solenoid B is equal to mu naught Ni. Now a question is coming in my mind. For the current it is okay, no problem. But what is the importance of number of turns? It says if number of turns are more, then magnetic field is more. Is it like that? Obviously. Because if on the same cylinder, rather than these 4 white wire turns, if there are 10, 20, 30, 40 turns, obviously the intensity of the magnetic field on the axis of this hollow cylindrical solenoid is going to be same. One more thing that I would like to mention over here, that is a term normally mentioned in your books, straight toroid. Toroid. What is toroid? It is something which is not associated with tortoise anyway. Toroid is, consider this solenoid once again, but now this time let us say rather than cardboard I am using a hollow soft plastic pipe, rubber pipe, fine, I can use that, no problem, and then 1, 2, 3, 4, 5, 6, 7 thousand turns. So now I have a long solenoid and that can be turned. I cannot turn this cylinder, it will break down like this. So you can turn this solenoid once, twice, thrice, 4 and so on. So toroid is what? It is effectively arrangement of solenoid in another solenoid, fine. So this is the way of defining this toroid, and over here the magnetic field is going to be similar in terms of this toroid or solenoid. So students, this was the basic explanation of Ampere's circuital law and 1 or 2 simple examples, fine. Basically this law is simply important, that is integral, closed integral, very careful, closed integral B dot dl is equal to mu naught I. Application part, in the coming videos I will provide you some collection of questions. I think then you will get the much better understanding of this application, fine. 2 I mentioned just for the sake of some examples. So with this I would like to say, keep revising, keep enjoying, take care of yourself. Thanks a lot for watching the video.